Alright guys, this once again is a video to explain how to do some of the gas law problems. You should have your in-class gas law problems in front of you. If you don't have it, just get a new one from the Weebly. If you're at home, you can do that as well. And that way, you can kind of run through some of the examples with me as we're going through. If you wanted to, you can try the examples first, and that way you can kind of then watch the video and see where maybe you got stuck. Okay? Alright. So as you're doing these examples, the most important thing to do is to try and determine, first of all, what type of equation you're going to be using. And so that's what's helpful by looking kind of like in the actual problems. So for example, I can kind of see that I have 1 liter there. Let me put a pen on here. Okay. So if I have 1 liter of a gas at standard temperature and pressure, that is going to be something that you're going to need to know. If you don't know it, I mean, I did put it on the bottom of the page, so you should be able to see what standard temperature and pressure means. All right. So this problem says 1 liter of a gas at standard temperature and pressure is compressed to 473 milliliters. All right. And we're looking for the new pressure of the gas. Okay. Well, you'll notice first of all that it doesn't really say much about the temperature. The temperature is kind of held constant. So I can see that it doesn't say the temperature changes, so I know that this is constant, which means it's not going to be part of the problem. So if it's not part of the problem, then I'm looking at an equation that just has pressure and volume. So if you were thinking of just pressure and volume, go back to your notes if you need to, and you could see that we're going to be using Boyle's law. So what I would do first is I'm just going to write out Boyle's law. P1 V1 equals P2 V2. All right. So I can see that I have a couple different things in here. First of all, it says standard temperature and pressure. And if I'm looking at standard temperature and pressure, the standard temperature is given in terms of degrees Celsius, but also given in terms of Kelvin. The standard pressure is going to be 1 atmosphere. Okay, and you should see it at the bottom of your page. So I know that my P1, if I labeled them, is 1 atmosphere. And my V1 is 1 liter, because it says 1 liter of a gas at standard temperature and pressure is then compressed. So once it does something compressed, then I know that that's my V2. My V2 is given as 473 milliliters. Uh-oh. This is the very first problem, aside from the notes, that I can see that my volume units don't match, and I need them to match. So if I have liters and milliliters, there's a couple different ways you can do it. One is you can convert milliliters to liters. The other, you can convert liters to milliliters. Your choice. What I would recommend is I would probably just convert this one to milliliters, because then you don't have any decimals, and I know some of you don't like decimals. So remember, you could go to your chart thing. Liters is in the middle, the capital U. Milliliters would be the little m off to the right-hand side, and you'd be moving it over 3 decimal places to the right. So that would make this 1,000 milliliters. All right. And the last one then, we would ultimately need to have P2, and it says what is the new pressure, so that is our question mark. Alright, so let's plug in our stuff. P1 is 1, V1 is 1, that doesn't happen often, P2 is our unknown, and V2 is 473. Hopefully some of you noticed that I made a mistake, and I put in 1 for my volume when we know it's not 1 anymore. So I'll go ahead and erase both of these, and I'm going to redo that. I was looking here. Okay, so pressure once again is 1 atmosphere, but our volume is 1,000. There we go. Okay, so we have 1,000 equals, and what I like to do, and I mean you don't have to do this, is I like my constant in front of my variable, so I know that it's P2 times 473. So I'm going to put the 473 in front just because I like to do my constant and then my variable, which means that P2 is going to be equal to 1,000 divided by 473, because I would have to divide both sides by the 473. So 1,000 divided by 473 gives you a value of about 2.11. So I would say 2.11. And the units, once again, we go back to atmospheres in our P1, and so that's going to be my unit for P2 as well. All right, that's problem 1. So these are the types of problems that you will see. You'll have some of these on your Chapter 3 test. All right, let's check out number 2 and see if we can figure out what equation it is. So if I initially have a gas at a pressure of 12 atmospheres, a volume of 23 liters, and a temperature of 200 Kelvin, and I then raise the pressure to 14 atmospheres, increase the temperature to 300 Kelvin, we're looking for the new volume of gas. And some of you probably immediately see exactly which equation this would be. You're like, oh my gosh, there's a lot of numbers in here, and I can see that the pressure changed, the temperature changed, and the volume is going to change. So that means that we're going to be dealing with the combined gas law. So that means I need P1, V1, and T1. And I'm just going to write them all in the same order this time. P2, V2, and T2. Okay. So it says initially have a pressure of 12 atms. The initial volume is 23 liters, and my temperature is in 200 Kelvin. It is already in Kelvin, so we're good. No conversion. Pressure 2 is 14 atmospheres. Temperature is 300 Kelvin, and it says we're looking for a new volume. So we write down our equation, P1 V1 over T1 equals P2 V2 over T2. So notice it has to be the combined gas law because you need all 3 of those variables. So we can plug in our numbers. So P1 is 12, V1 is 23, and T1 is 200 equals P2 is 14, V2 is our unknown, and T2 is 300. You guys remember what to do here? So I have all these numbers. Once again, there's 2 things you could do. You could either kind of do the left side by itself and then algebraically solve by multiplying by 300 and dividing by 14, or you can cross multiply. And once again, I'll cross multiply just so all these problems kind of work all the same. So I'm going to do 12 times 23 times 300. And in doing so, I get 82,800. So that was once again cross multiplying over there. And then I set it equal to the other cross product. And I can see I'm going to do 200 times 14. So I have 200 times 14, and that gives me 2,800. So I have 2,800, lots of 2's and 8's in this, and that's times V2. So lastly, I'm going to divide both sides by 2,800, and so I have 82,800 divided by 2,800, and that's going to give me thereabouts 29.6 liters. And I know it's liters because, once again, I'm going to come up here and I see that my unit on V1 is liters. All right, 2 down, 6 to go. All right, a man heats a balloon in the oven. I don't know who heats balloons in ovens, but this guy does. If the balloon initially has a volume of 0.4 liters, so that is a volume, V1, and a temperature of 20 degrees Celsius, Celsius, then what will the volume of the balloon be after he heats it to a temperature of 250 degrees Celsius? And it says nothing about pressure in the problem, so I'm probably ignoring pressure, which means I'm dealing with volume and temperature. So I'm going to write V1 and T1 and V2 and T2. So a lot of times I'll try and say something about like pressure held constant, and these ones I just left them out, I guess. Alright, so volumes, these ones are easy. 0.4 liters, and the other volume is what we'll be looking for. The temperatures, on the other hand, we got some issues because they're in Celsius. So this one's 20 degrees Celsius. And so do you guys remember how to go from Celsius to Fahrenheit? I'll go ahead and write it on the top here. So if I wanted to get Celsius to Kelvin. If I wanted to get Kelvin, then I know that I have my Celsius, and I'm going to add what to it? Still waiting. Good. You're going to add 273. Don't forget about the decimal, 0.15. All right. So I'm going to add 273.15, and that's going to give me 293.15. Okay. Let's split that a little bit. All right. T2 is 250 plus 273, so we'll do that one instead of actually, writing it down. All of it plus 250. Wow. So that's going to be a big number. So it looks like it's a huge temperature just because it's in Kelvin. So 523.15 Kelvin. All right, and I could put my Kelvin unit on there too. All right, so I see that this is volume and temperatures, which means that we are dealing with Charles' law. So this is V1 over T1 equals V2 over T2. All right, so I'm going to plug in my numbers. V1 is 0.4. T1 is 293.15 equals V2 is my unknown and 523.15. And some of you might be asking, like, why do I have to use Kelvin? Why can't I use Celsius? And the reason is because some of the other variables that are actually not in this equation, for specifically there's a constant that's kind of part of these equations as well. It's based off of this unit of Kelvin. So if you had Celsius in there, your units wouldn't cancel out, and so you couldn't actually create these equations. All right. Or you could, you just have to use a different constant. So I have 0.4 times 523.15. And in doing so, I get 209.26. And once again, I was doing the cross product of those two. And then I'm going to set it equal to the cross product there, which should be a little bit easier. 293.15, and this is times V2. All right, so all you got to do is divide by the 293.15, and you should end up getting a decimal because one was bigger than the other, so we get 0.71 liters. Once again, this one's also in liters because my original was in liters. All right, so we've done Boyle's law, we've done combined gas law, we've done Charles' law. Let's try another example. Submarines need to be extremely strong to withstand the extreme high pressure of water pushing down on them. An experimental research submarine with a volume of 15,000 liters, so there's our V1, has an internal pressure of 1.2 atmospheres. Atmosphere is the unit for pressure, and it also says pressure. If the pressure of the ocean breaks the submarine, forming a bubble with a pressure of 250 atmospheres pushing on it, how big would that bubble be? Interesting. Okay, so we can see that our pressure is changing, and we're looking for how big the bubble would be, which means it's going to be a volume. So we're dealing with pressure and volume. Can you guys tell me which equation uses both pressure and volume? And Boyle's law. So we're going to use Boyle's law again, and so our initial pressure is 1.2. I'll leave off the units this time. V1 is 15,000. P2 is 250. And V2 is our question mark. So remember, Boyle's law is P1, V1, so they're beside each other, and P2, V2. And there's a multiplication between those. So pressure 1 is given as 1.2. I'm going to go ahead and write volume 1 first, 15,000. And then that way I can put the 1.2 for spacing purposes. And P2 is 250 times V2. So I'm going to take that 15,000, I'm going to multiply it by 1.2, and that's going to give me 18,000. And this side really doesn't change, and my variable was actually after my constant, so I was already happy. And last step, we're going to divide both sides by what's in front of the variable, so the 250. So my V2 should come out equal to 72, and the units once again was liters. So this bubble, with all that extra pressure, really got compressed from 15,000 liters all the way down to 72 liters. All right, moving on. A gas has a temperature of 14 degrees Celsius. It's in Celsius again, so remember we got to add that 273.15 to both the 14, and I can see there's one for 29 as well. So gas has that temperature and a volume. If the temperature is raised and the pressure is not changed, see, that's what I mean, I'll try and write them like this, then what is the new volume of the gas? So we are dealing with relationship between volume and temperature. Okay, so my original temperature is 14, but adding 273.15 to that is going to give me 287.15. The volume originally is 4.5, and the other temperature was originally 29 degrees Celsius, so therefore that's going to be 302.15 Kelvin. And we're looking for V2. Remember, this is Charles' law this time, so it's V1 over T1 equals V2 over T2. So you'll notice if you're ever given temperatures, it's always in the denominator. Pressure and volume are always on the top. And let's see, so we're going to plug in 4.5. We're going to plug in 287.15. And that's equal to V2 all over 302.15. Okay, so we get to the same point again. We have a proportion we're going to cross multiply, so I'm going to have 4.5 times 302.15, and that's going to give me, a number. It's going to have a decent decimal, so it's 1,359.675. Might as well use it all so you don't lose any, values, and it doesn't round off. And that's equal to 287.15 times V2. So remember that we're going to divide by the 287.15 because it's in front of the variable. And as we do so, 287.15, that's going to give us about 4.7, if we do the rounding, 4.74. And once again, the units are liters. So you notice that we didn't change the temperature a ton, like 15 degrees Celsius. And so you can see that the volume actually then increased by just a little bit as well. All right, number 6. Have an unknown volume of gas. So originally, check this out. You have the unknown volume of gas, so that's your V1. At that pressure, so there's your P1, and a temperature, so there's your, P1 and there's your T1. If I raise the pressure, so now we're raising the pressure to 1.2 atmospheres, we are decreasing the temperature by 5 degrees, or not degrees, but 5 Kelvin, and our final volume is now 48 liters. We're looking for the initial volume. That's different. Normally we've been looking for the final, so this one's slightly different. You'll also notice that it has all the variables, so P1, V1, and T1. And we got P2, V2, and T2 as all of our values there. And so we can start kind of filling stuff in. So our initial pressure is 0.5. Our initial volume is our unknown, which is different. We have 325 K. Our final pressure is 1.2 atmospheres. It increased. Our final temperature is 320, and we're given 48 liters as our final volume. So this is combined gas loss. We have P1 V1 over T1 equals P2 V2 over T2. So I'm going to plug stuff in. So we got 0.5. V1 is our unknown over T1, which is 325, equals P2 1.2, V2 48, and T2 320. All right, lastly then, cross multiply. So remember, this one is the one where you can rearrange. So I'm going to do 0.5 times 320, 160, V1. And then I'm going to do 325 times 1.2 times 48. And that gives me a value of 18,720. So naturally, we're going to divide by the number that precedes the variable. So I can see I have V1, and I'm going to divide by 160, which is going to leave me with 117. It actually comes out exactly 117. And remember that the units are liters for that. All right, 2 to go. Okay. So we got a soda bottle is flexible enough that a volume of the bottle can change even without opening it. Interesting. And you guys have probably done this. You like squeeze a water bottle, you can change it. So if you have an empty soda bottle, so it's a 2-liter bottle, at room temperature, which is 25 degrees Celsius, we're looking for the new temperature if you put it in your freezer, compressing it to 0.85 liters. So notice that we're not going to change the number of particles, and we are also not changing the pressure. We're going to assume that the pressure is constant. Okay, so we are dealing with a change in volume and a change in temperature while holding pressure constant, because I didn't talk about pressure at all. V and T, that's Charles' law. So remember, our initial volume is 2 liters. 25 degrees Celsius has to be converted. So once again, to convert that, you're going to add 273.15, and that would give you 25 added on to 273 makes it 298, and then 0.15. All right, V2, you're at 0.85 liters, and naturally we are looking then for the new temperature, which would be T2. All right, so this is Charles V1 over T1 equals V2 over T2. All right, just plug them in. 2 over 298.15 equals 0.85 over T2. And check this out. If you really wanted to, you can kind of see, from 2 to 0.85, that's decreasing, so I should get a number that's less than 298.15. So let's cross multiply first. So I'm going to have 2T2 equals 298.15 times 0.85, and that gives you a value of, hold on, let me try that again. So 298.15 times 0.85, and that gives you 253, write it in, 253.4275 if you wrote out the whole number. At least on my calculator, that's what I got for, yep, that is the whole number. Okay, and then I'm going to divide that by 2, and it's going to give me a very fantastic number. So T2 equals 126.7. And this is temperature, and temperature for us was measured in Kelvin once we converted it, so that's in Kelvin too. So 126.7 Kelvin. All right, last one. If I have 2.9 liters of gas at pressure of 5 atmospheres and a temperature of 50 degrees Celsius, what will be the temperature of the gas if I decrease the volume of the gas to 2.4 liters and I decrease the pressure to 3 atmospheres. So you'll notice that I actually didn't do any of Montan's laws in this gas law practice, but remember that if I had no volume, then I'd be using a Montan's law. Alright, so in this one I'm given a volume, 2.9, I'm given a pressure of 5, and I'm given a new temperature in Celsius. So once again, we got to change that. That'll be 323.15. And what will be the temperature? So we're actually going to be looking for T2. Decreasing the volume to 2.4 and the pressure to 3. So we're going to write our equation, P1V1 over T1 equals P2V2 over T2. So our P1 is 5 and V1 is 2.9, and I'm just looking at my knowns on the left hand side. 323.15 equals P2 is 3, V2 2.4, and T2 is unknown, so we'll leave it as T2. So we cross multiply, so we have 5 times 2.9, which is 14.5, and then remember that's times T2, equals 323.15 times 3, and then times 2.4. So we get about 2,326.68. T2 is here, it's multiplied times 14.5, so I'm going to divide both sides by 14.5. And it gives us about 160 point, I'll round it to 0.5 because it was at 0.46. And once again, temperature is measured in Kelvin, so that is also now Kelvin. And that's that. So when you're looking at these, once again, you want to look at what values you're given. You want to look and see if you need to convert any of your temperatures, and then you just find the equation you need and plug them all in. For your test, the equations will be given to you. I will not tell you which one is which because I might ask questions based on that, but ultimately you have the equations available. As long as you know what the units of different stuff would be, you should be able to then fill them in. All right, that is the end of your gas laws in